So instead of doing it this way where we test all of them to figure out which one works, we're going to let our calculator help us. We're still going to list out the possibilities, but then we're going to look on our calculators which one actually shows up on the graph as a true possibility. So that's what we're going to do in the next example. First thing we're going to do is still list out the possible zeros. Factors of p. What are the factors for p? Plus or minus 1 and plus or minus 13. That's it. And factors for q.
1.
Plus or minus 1. So we just get plus or minus 1, plus or minus 13. Those are our possible answers. So now we're going to graph it on the calculator. And you're going to find the 0 from the calculator. So this is my shortcut today. So let me pull up the calculator. So all we did is we put this in the calculator. We used menu 6, number 1 was 0. We found the 0 from our calculator. Now we have to take that equation at the top and we need to break it down. So now using that 0, the 0, what did we get from the calculator? Which one of those did the calculator tell us works? 1. That you have to do synthetic division with.
Okay.
So we're going to put 1 in the box here. And then we're going to go ahead and divide. So that's going to be 1, 1, negative 5, negative 5, 17, 17, negative 13, 0. Here's where this one is a little bit different. If I were to write out the answer right now, what degree am I going to start with? I'm going to start x cubed, right? So this right now is x cubed minus 5x squared plus 7x minus 13. Do we have a method to solve that? No. We have to break it down again. You have to do synthetic division until you get a quadratic equation. So if we look back at our graph here, were there any other zeros on this graph?
No.
There weren't any other zeros on the graph. But if you look at it carefully, the fact that it bounces tells us something. Do you remember what it bounces tells us about the multiplicity? This is actually what we call a double root. It has a multiplicity of 2, which means we can use it twice. If it didn't have a multiplicity of 2, you could only use it once. You'd have to look for another one. There's going to be another one we look at in a minute that's going to have another root. But because that one bounces, that tells you it's a double root, you get to use 1 twice, because 1 is an answer 2 times. So we're going to use it twice. So you're going to divide by negative 1 again, but now using these new coefficients, 1, negative 5, 17, and negative 13. So we bring down the 1. 1 times 1 is 1, negative 4, 13, 13, 0. Now, what can we write for that equation? Now that we divided the cubic one, what's your degree going to be now? X squared. Because we divided twice, it now took our x to the 4th and breaks it down to an x squared. So that's kind of something to be aware of. If it's an x to the 4th equation, you have to do 2 rounds of division to get down to the quadratic. Does that make sense? Then we have to solve this. Set that equal to 0. Are there factors of 13 that add to negative 4? No. So then what? No. It's a quadratic. You can solve every quadratic. So this didn't work. What do? You do the quadratic formula. When in doubt, the quadratic formula will always work. So if you check factoring and factoring doesn't work, you can use the quadratic formula because it's a quadratic. Right? X equals negative b plus or minus square root of b squared minus 4ac all over 2a. So then I get 4 plus or minus the square root of, that's 16 minus 42, no, 52, negative 36 over 2. Square root of negative 36. 6i. And both of those are divisible by 2, right? Just make sure you do both of them. If you need to write it like this first, this is usually how your book splits it up first. And then we divide both of them by 2, so it turns into 2 plus or minus 3i. So then what are my zeros here? Well, we just got, right? How many zeros does that count as? 2. The plus or minus sign tells you that's 2 answers. And what else was my 0? The 1, and technically didn't they have a multiplicity of 2?
Yep.
I'm going to write that in, because if you look back at your degree, and I have this as a note later in the side, but if you look at your degree, it was to the 4th power. You should be able to count 4 answers at the end. So because it has a multiplicity of 2, that counts as 2 answers. And then the plus or minus sign counts as 2 answers. So that right now, it doesn't look like 4 answers, but that's really 4 answers to our polynomial. Does this make sense? Should hopefully, we did something like this last year. They're a little bit harder than what you did last year, though. So the next slide, it just explains to you what I just said, is that the number of roots should equal the degree of the polynomial. That's if you count the multiples separately. So with that 1, since it happened twice, if I count it separately, I got to my total of 4. So that's a really nice way at the end of the problem to check. Especially if you do something like take a square root and you forget to put a plus or minus sign, then hopefully you'll go back and remember to put the plus or minus sign so you have the right number of answers. The second part is really what we're going to talk about on Monday. It has to do with a complex root. If a plus b, I, is a root, then its conjugate, a minus bi, is also a root. So every complex imaginary root will occur in what we call conjugate pairs. So that's what we're going to deal with on Monday. And then we do have one more thing to learn. Descartes' rule of sign. Has anybody heard of Descartes before?
He does too much.
He does. He actually did a lot in his lifetime. He was a philosopher, but he also delved into math a little bit. Have you ever heard of the Cartesian plane?
Yes.
Do you know what the Cartesian plane is?
Yes, it's a simple XY graph.
It's a simple XY graph. That's just a fancy word for the graph that you. But he's the one that came up with the graphs that we graph on. That is his Cartesian plane. So Descartes' a pretty cool guy. I learned a lot about him in college in my philosophy classes. So he did a lot. He has very logical ways of thinking through things. So he's kind of cool. What he says is that if you look at a polynomial function, you can determine how many positive real zeros you're going to have and how many negative real zeros you have, just based on looking at how many times the signs change. For positive real zeros, we're going to look at the sign change in the original function. For negative, you're going to have to plug in negative x first, kind of like you're trying to decide if it's even or odd. But then you're going to look at how many sign changes that has. The other thing that it says is, for instance, if I get that there's 4 positive answers, that it could be 4 or any even, if you go down by 2 pretty much from there, any even integer after that. So if it's 4, it could be 2 or 0. If it's 3, it could be 3 or 1. So we're always going to go down by 2 until we hit 0. All right, so if you look at number 1, I was trying to think of a way to have you guys look at this, and what I came up with is first, when you're doing the positive one, just look at the signs. I'm just going to write the signs down of that original equation. So it's positive, negative, negative, negative. You're looking for it when it changes. How many times does it change? Doesn't it only change right here? That is not, that's the eraser. Dang it. Where's the highlighter? There's the highlighter. It just changes here, right? That's not a great highlighter. I do not like writing in here, but it's the best place to record it. So it changes there, right?
Yes.
I'm just going to circle it.
Recording it?
Yeah.
So am I.
Changes there, right? So that's 1. That means there's going to be 1 positive real root. So what this helps with is if we went back that very first problem that we did without putting it in the calculator, before they had calculators, this would at least tell you, oh, I should probably check all the positive ones because there's exactly 1 positive real root, so I know that that's going to help me out here. So that this is kind of, it narrows down your choices from that first one. All right, for the negatives, the first thing you have to do for the negatives is you have to figure out what f of negative x is. So you got to write it out. F of negative x is going to be negative x cubed minus 2 times negative x squared minus 7 times negative x minus 4. So that's going to turn into, the first one's going to become negative. The next one's going to stay the same, so it's going to stay negative 2x squared. With evens, they're going to stay the same. Odds, they're going to change. Evens are going to stay the same. The next one should be plus 7x and then minus 4. So then write out those signs. It goes negative, negative, positive, negative. How many times does that change? It changes here and it changes here, right? So that tells you there's 2, or if you can subtract 2 from that number and it's still not a negative answer. It's still a number that you could have when you're counting. It counts. So 2 or 0, negative. Real roots.
Why is it 2 originally?
Oh no. Yeah. You have to go down, if you can go down by 2, that's another possibility. Because what we also have to factor in here is that you could have things that are not real, right? So it could be 2 real roots or it could be 2 imaginary roots. So it's 2 or it's 0. Because this kind of goes back to that idea, I know, and this is very like theoretical math stuff, but it goes back to that second part on the last slide where it talks about how you have complex roots come in pairs. So there could be 2 real ones, or there could be 2 imaginary ones. So if there's a pair of imaginary answers, we're going to always decrease by 2 to account for they could also be imaginary. So there could be 2 negative numbers, or the 2 other answers we're looking for could be imaginary, so then there would be 0 negative real roots. So what we're really accounting for is the imaginary ones that we're not really thinking about yet. Does that make any more sense? You're just always going to go down by 2. Because you're accounting for the fact that there could be complex roots. Do you want to try number 2? I'll give you a minute. Try number 2. So we wrote out the signs. It changes 4 times. So that's going to be 4. Or you're going to go down by 2. Or 2 or 0. If you can go down by 2, you're going to write that number as well until you get to 0. 4 or 2 or 0, positive real roots. That tells me how many positive real roots I have. And this is just practicing this. We're going to do more with this on Monday, and I think it'll make a little bit more sense, but if you can practice looking at your sign changes. And then for the negative, you had to do f of negative x. When I plug in negative x to x to the 4th, it stays the same. But then this one's going to change because it's odd. This one's going to stay the same because it's even. This one's going to change because it's odd. So if we look at those signs, they're all positive, aren't they? Did it change at all?
No.
So what does that tell me?
0.
You have 0. 0 negative real roots. Does that make sense?
Yes.
So that at least, if you were doing this back in Descartes' time, if you were trying to solve this, you didn't have a calculator to graph it. You actually didn't even really know what this graph probably looked like. You could literally eliminate all the negatives from the list of possibles. That's what this does for us. Is it says there's no negatives, so I just need to check the positive ones and see if any of those work. Yeah. We good?
Yes.
That's it?